All right, so let's talk about acid-base, okay, and the balance. We dealt with fluids, we dealt with electrolytes, now the acid-base, which is the biggest section. So I'll do a little bit today, and we'll do a little bit on Wednesday, okay? Some basics, okay? An acid is anything that's going to release hydrogens, right? Old news to you guys, okay? The more hydrogens, the more acidic that is. A base is anything that removes hydrogen, so there's less hydrogens in that solution. If there's really few amount of hydrogens, then it's going to be a stronger base. So what you got to look at over here, all right? A strong base is going to make, let's say, hydrochloric acid. When you put hydrochloric acid in water, it will dissociate completely. It will change to hydrogen ions and chloride ions, and it's 100%. So what I'm trying to show you over here is that hydrochloric acid, when put in water, you will get hydrogen ions and you'll have chloride ions. 100% goes here, which means that there's going to be 0% over here. It's a complete association, and you can tell by the yield sign, it only goes one way. That's what makes this a strong acid, because 100% has actually been converted into this. But then we have a weak acid. A weak acid is what we've been talking about mainly. And I'll just draw part of it here. Carbonic acid. I'm just not putting the carbon dioxide and the water on the side over here. But what happens in this case is that carbonic acid will partially dissociate. You're only going to get 50% of this, but you'll get 50% that stays in this area here. And that's because this yield sign goes both ways. It's reversible. That's not reversible. This will lead to this is a strong acid, this is a weak acid. So if you put more hydrogens here, it goes this way. You put more acid over here, meaning more carbonic acid, it'll go this way. If you put more hydrochloric acid over here, it's going to go here. You won't have any hydrochloric acid in it. Does that make sense? You see the difference between a strong acid and a weak acid. Okay? It's similar to a base, but I don't want to talk too much about bases. Okay? Since we're more of an acidic kind of theme. Okay? All right. Now, the sources of hydrogens, where are they coming from in our bodies? Okay? There are a few different places. All right? We could have them from our respiration, whether aerobic respiration or anaerobic respiration. And we've been talking about these throughout the past few weeks in terms of carbonic acid or lactic acid. We also have other places that are happening throughout our systems we didn't really stress so much about, but they are there. All of this will add to the hydrogens in our body. So we have things called volatile acids. Volatile acids are acids that can actually leave our body into the environment. Okay? So a good example is our good old carbonic acid. That can get changed to carbon dioxide, and we could blow that off, and it goes into the atmosphere. We also have fixed acids that don't leave the solution. Once they're produced, they remain in our body fluids until the kidney can actually get rid of them. All right? And this is sulfuric acid, phosphoric acid. These are other things that we really need to talk about much. And then we have organic acids, and these are acids that, well, they're byproducts of usually some sort of metabolism, usually anaerobic metabolism, things like lactic acid and keto acids. Remember what keto acids are, and we'll get into it, but we dealt with it when we dealt with diabetes. Ketoacidosis is a good example, but keto acids are a byproduct of fat metabolism. Okay? So there's our wonderful reaction, right? We've been dealing with this for easily a month, okay, if not longer. But these are the places that we see it. We see this acid or this enzyme that does this reaction. We see it in these areas here, right? found in the blood-brain barrier, right? You have to have carbon dioxide come in. Carbon dioxide can't get into the brain, so we get carbonic acid at the blood-brain barrier that converts it into hydrogen ions. Now the hydrogen ions can go in and could cause us to breathe. All right, goes to the respiratory centers in our brain. It's in the parietal cells of our stomach to make hydrochloric acid. It's in the pancreas because we need to make bicarbonate so that when the acidic foods leave the stomach and go into the duodenum, we're going to need secretin, a hormone, that is going to stimulate the carbonic anhydrase in the pancreas to make bicarb. And the bicarb gets added to this chyme that just left the stomach that's very acidic, and it neutralizes it. Remember, secretin is our natural antacid, and that's how it does it. It's in our red blood cell, and you've seen that, so that most of our carbon dioxide that's in our body is transported in our blood as bicarb ions. All right, about 70% of our carbon dioxide is passed through our plasma as bicarb ions, and it needs to change back into carbon dioxide by the time it gets to the lung so that we can breathe off the carbon dioxide. And then, of course, we've been talking about in the kidney where carbonic acid is, carbonic anhydrase is located in the kidney also. Okay? So these are all the places, and this is, so like I always told you, if you're looking for a tattoo to get, you probably want to get that one. I'm not encouraging any tattoos, but what I'm just emphasizing is that this is a pretty important reaction you need to really know and break down. And you should know it, all the different charges and stuff. Hint, there might be a time where you might have to reproduce this on a test paper, okay, this whole reaction. All right, now, let's talk about this, and I'm not going to go into details about Henderson-Hassalbach, but if you understand this concept, it's going to make you to understand acid-base balance much better and how our bodies will compensate using the lungs and the kidneys. I'm not going to ask you to memorize this formula. I want you to just understand where it's coming from, so it makes your life a little bit easier. We have a blood pH, and the blood pH is 7.4. Okay? That's what our average is. So it's slightly basic, our blood, right? The 7.0 is not. It's really a range. We have it anywhere from 7.35 to 7.45 with an average of 7.40. Now, how did we get this? How did we figure this out? Well, the pH is something called the constant, which is the pK, which you don't have to worry about. And then the log of the concentration of bicarb, when you have it in brackets like this, it means concentration over the partial pressure of carbon dioxide. Now, I'm going to make this very simple for you to really understand. You don't have to worry about this log and stuff. But if you know anything about math, when you have log of something, it's always the log of 1. Meaning that if I have the concentration of bicarb over partial pressure of CO2, this is equal to 1. Okay? This is not a math course. I'm not going to go into what log means and stuff, but that's what we're saying, is that this equals 1. You're on the same page with me? But I could write this by saying 1 over 1. Isn't that the same thing? Okay? Isn't it the same thing if I do 4 over 4? Doesn't that still equal 1? You agree with that? Okay? So, this is what's going to happen. If we have bicarb, and for some reason the bicarbonate goes down to, it decreases to 2, then what must the PCO2 do to make this back into 1? Go down. Then this has to go down to 2. Does that make sense? Let me ask you this. Bicarbonate. What organ is going to get rid of bicarbonate? What organ? It's an ion. It's water soluble. How do you get rid of bicarbonate? Kidneys. This is CO2 gas. What organ is going to get rid of a gas? Lungs. So look what's going to happen here. All right? We'll do this one again. If this is 4 over 4, we'll just use that as an example, and my carbonate increases to 10. Okay, my bicarbonate increases to 10, not bicarbonate, I'm sorry, my carbon dioxide increases to 10. Then what organ is going to compensate to get this to 10? The kidneys. Does that make sense? So if this goes up, then my kidneys have to reabsorb bicarbonate to get it back into the bloodstream so that we can actually increase this to 10. So that we become 1 again. Does that make sense? All right. Likewise, let me just make sure you understand this concept. If we had this at 4 and 4, and we have for some reason the bicarbonate is increasing to 6. What organ is going to compensate this? The lungs. And what is the lungs going to do? Is it going to hypoventilate or hyperventilate to keep more carbon dioxide in your bloodstream? Hypo. You're going to breathe slower, which means that this is then going to, the carbon dioxide in your bloodstream is going to increase to 6. You see what's going on? Does that make sense to you? Okay? And it's all because this equals 1. But that's what we're going to be talking about throughout the next couple of days, is compensation. You never thought that kidneys and lungs had anything to do with each other until you entered A&P2. But they have a lot to do with each other. Okay? We clear with that? Okay? So again, if you increase the CO2, then we have to increase the concentration of bicarb, and vice versa. This decreases, then this has to decrease. And it's all because this is equal to 1. Okay? I'm not going to ask you to regurgitate this formula. It's not about that. It's the idea of where this is coming from. We clear with that? Not too bad? It's immunology put to shame, though, right? Okay. All right. The plasma concentration of hydrogens. Okay? The way they figure it all out is through here. I'm not going to ask you to calculate this. I just want you to understand that the concentration of hydrogens in our bloodstream is about 40 milliequivalents per liter. You should know that number, all right? Especially when you go into other fields. They're going to be using these numbers. If it's too high or too low. Well, let me tell you this. If I see a plasma concentration of hydrogen ions as 60 milliequivalents per liter, is that acidosis or is that alkalosis? Is your body more acidic or more alkaline? If you have a concentration of hydrogens of 60 milliequivalents, is that an increase or a decrease? It's acidic. It's more increased, right? That's how you're going to use this. That's why you should know what the normal is, and then you can play with the numbers if they're too high or too low. All right. So again, normal levels, the pH in the blood, all right, the plasma, 7.4 with a range of 7.35 to 7.45. And the concentration of hydrogen should be about 40 milliequivalents per liter. Any change in this, your body will seriously feel it. But if you've got good kidneys and good lungs, it'll compensate. Okay? Now, the body seems to be going through more acidic stresses than basic stresses. Your body's always producing amino acids or breaking down proteins to amino acids, fatty acids, lactic acid. So our body ends up going through more acid stress than basic stress. Does that make sense? Okay? So we have a lot more of that going. Now, there's diseases that would actually cause you to have a basic stress, your body has to compensate. But I'm talking about a normal, healthy person, day to day. We have more acid stress in our body than basic stress. Let's talk about buffers. Buffers is any system to make sure that the pH doesn't change. And we basically have this. Right? Our wonderful reaction is a buffer. So that we have 50% on both sides so that our pH doesn't change. All right? I'll write it up here again. I'm using it. Right? This is a buffer. Remember, it's got to be 50% over here and 50% over here. If we add more hydrogens here, what's that going to do to the pH? If we add more hydrogens in the blood, pH. pH goes down. I know it's one of those things you've got to memorize. As hydrogens go up, pH goes down, right? It becomes more acidic. So we don't like that. This is a whole buffer system. You add more hydrogens, the pH changes. But the buffer is going to make it go this way so that the hydrogens go down and then the pH doesn't change. You see what's going on? That's what a buffer is. It resists any kind of change to the pH. This happens very rapidly. Okay? If we subtract some of these hydrogens, they go out in your P. Then there's going to be less over here, and there's going to be more products here. So the reaction is going to go this way until it fills up. Does that make sense? Right? We've been working with this. But that's what a buffer is. Okay, so it's any substance that's going to minimize any change to hydrogen. Okay? And this reaction is a buffer. There's a lot of buffers in our system, but this is a buffer. So here's the lines of defenses for our bodies to try and increase hydrogen concentration, or really to make sure that the pH doesn't change. So we have these things going on. Our first line is going to be this buffer. It happens very quickly. You add hydrogens over here, it goes this way. You add carbon dioxide over here, it goes this way. Very fast, so that it becomes 50-50. So this happens in seconds. All right? But it's only partial compensation, meaning this happens very fast, but it doesn't last for very long. We have to have another system that's going to last a little bit longer. But we can't eliminate the acids. We need something else. In other words, if it goes this way, it turns into carbon dioxide. We need some other organ to get rid of the carbon dioxide. You know where I'm going with this, right? So this is the first line of defense that happens in the blood. Our second line is going to be the lungs. Once this happens, we start building the CO2, the lungs have to take the CO2 and blow it off. So it gets out of your system. This can eliminate the acid out of your bloodstream, but blowing it off. We're not getting the CO2 staying in there. But this is still an incomplete. It happens in minutes, but you can't blow it off for a very long time. Your body, the amount of acid that comes out, or the amount of this reaction that's going to happen here, is going to go faster than what your lungs can actually do. So we got to have another system. This is better than the buffer system because it's actually eliminating it, the carbon dioxide or the acid itself. But we need something that's going to last longer. So we have a third line, and that's our kidneys. The kidneys will get it right out of the system, do a whole bolus of hydrogen to get it right out. The only thing is, it takes a long time. All right, it can take hours to a day. Does that make sense? All right, this is the best system, and it will eliminate things directly. But this is a complete compensation because it eliminates those ions right out. So these are three ways we can actually get our pH back to what it is. If our kidneys are doing bad, our lungs will compensate. If our lungs are doing bad, our kidneys are compensated. If you become a nurse in your intensive care unit and you know someone's got emphysema and kidney failure, you know you're going to be with that patient for a very long time. You don't want to have other patients because you're basically screwed if you don't have your lungs or kidney. These people are usually on some sort of dialysis. There's got to be some sort of way to remove those acids if your body can't do it. Okay? So, regulation of pH, kind of reiteration of stuff we've been talking about. So, lung regulation. Lungs are going to remove volatile acids, all right? And it regulates the partial pressure CO2. If you hyperventilate, you're going to blow off more CO2. If you hypoventilate, then the CO2 wants to stay in your body. This starts building up, and the reaction goes this way. Does that make sense? Hypoventilation, hyperventilation. If you increase carbon dioxide in the blood, this goes up. For some reason, you hold your breath. Carbon dioxide goes up. The reactants over here increase. When these increase, the reaction goes this way, and your hydrogen ions would then increase. Does that make sense? And if your hydrogen ions increase, what happens to your pH? Goes up or down? Goes down. Okay? You hold your breath, your pH goes down. Okay? So breathe in slower, you'll hypoventilate, you're going to retain it. Your pH will go down. If you breathe faster, i.e. hyperventilate, you're going to remove more CO2, which means the reaction is going to go that way, which means that the hydrogens are going to go down, this is going that way, and then your pH goes up, because we're removing hydrogen ions. So if you think about this case, okay, the blood pH drops to 7.3. Remember, 7.35 is our lower marker. Anything less than that, you're in an acidic environment. How does the body compensate? Right? So, give me the answer. All right? So how does the body compensate? If your pH goes down, so in other words, these are increased. Okay, if you increase this, which means your pH is down, which means what that is, your pH is less than 7.35, then there's an increase to this. So which way does the reaction want to go? That way or this way? It goes this way. Are you making more CO2 or less? More CO2. If you're making more CO2, do you tend to want to blow it all off and hyperventilate, or you want to retain it and hypoventilate? You want to blow it off. So what will happen is you're going to hyperventilate to get rid of the carbon dioxide, because the reaction is going that way. Is that clear? Okay. Let's do this one. Let's say your blood pH rises to 7.5. How does your body compensate? That means basically this has decreased. Right? You're in an alkaline environment. This is decreased, which means your pH is up. So technically, you have more products here than you do over here. So to make more hydrogens, does the reaction want to go that way or that way? It's going to go that way, which means that do you want to blow off all the CO2 or you want to retain it? Retain it. You want to build this up to create this reaction going this way. Do you hypoventilate or hyperventilate? Hypo, right? You hypoventilate, keeping the CO2 in your blood for a longer amount of time to push the reaction that way so that your body adjusts it. This is the buffer system we've been talking about. Too much over here, the reaction goes this way. Too much over here, it goes this way. Too little over here, reaction goes this way. The buffer's fast, but you're going to need the lungs to really adjust it. And it's only good for a short amount of time. If you have too much of this over here, the kidneys have to get rid of it through the urine. Okay? So again, just to show you that if you increase the CO2, your pH goes down. That's what this is saying here. If you increase the PCO2, if this goes up, because you're hypoventilating, if this goes up, the reaction goes this way up, which means that your pH goes down. Does that make sense? Don't memorize. As I've always said, don't memorize. You're going to find yourself failing exams. Understand the concept that if your PCO2 goes up, the reaction goes this way, the hydrogens go up, which means the pH goes down. And vice versa. Clear with that? Renal regulation. Okay? Removes fixed acids. Reabsorbs bicarb. If you reabsorb bicarb, this is going to go up, which means net-wise, you're going to have a decrease of this. Yes? Because we're just reabsorbing this one. So therefore, you'll have a decrease of this, which means your pH goes up. More of an alkaline situation. Now here's some parts you kind of do have to memorize. For every sodium that gets reabsorbed, you secrete one hydrogen and you reabsorb one bicarb. Does that make sense? So bicarb and sodium are going one way, hydrogen's going the other way. During stress, aldosterone comes out. Comes from your adrenal cortex. When aldosterone goes out, it's going to reabsorb sodium. As sodium gets reabsorbed, bicarb will get reabsorbed also. It follows the sodium. When it does, you're going to develop an alkalotic situation. Because more bicarb goes up, that'll be net-wise, you'll have less of this. See how you put it together? This is just showing you in the proximal convoluted tubule here's the lumen of the urine inside where the filtrate is. And this is the bloodstream. This is one of the cells in the proximal convoluted tubule. And it's showing you where Ca is, that's carbonic anhydrase. Here's our wonderful reaction that I'm putting here is in our kidney. But you can also appreciate which way the sodium goes and bicarb. Notice sodium gets going this way into the bloodstream. Bicarb will also do that too. But the hydrogen ions are going the opposite way as the sodium. Okay? Again, just re-emphasizing The lungs and the kidneys are compensating with each other. It's just something from a coloring book I got just to emphasize again what the lungs are doing and what the kidneys are doing. They work with each other. And you could read that over here and what that is. All right, it's a little summary. Other factors that influence hydrogen secretion. Potassium. Blood potassium is also going to affect this. This is a key moment for you to understand. Hydrogen shifts in and out of cells in opposite directions of potassium throughout the whole body, not just the kidney, the whole body. And this will maintain cation balance. Think about it. Cation, the charge. As hydrogen goes in, that's making the bloodstream more negative then. So potassium has to go out. Does that make sense? To keep the charge equal. So they're going to go in opposite directions. So potassium enters the cells in exchange for hydrogens to keep the charge balanced where it's supposed to. So compensating hyperkalemia will cause acidosis. Look at the picture here. You have too much potassium in your bloodstream for whatever reason. So your body wants to fix that. So it's going to take some of the potassium and put it into the cells so that you have less potassium in the bloodstream. Does that make sense? That's how your body's going to try to compensate hyperkalemia. But that's going to make outside the cell less positive. So therefore, as potassium is going from the bloodstream into the cells, hydrogens have to be exchanged with it. So hydrogens go out into the bloodstream for every potassium that goes into the cell. So therefore, yes, we're correcting the hyperkalemia, but you're making your bloodstream more acidic because the hydrogens are going out there. Does that make sense? Can you visualize that? All right? So as kidneys try to fix this by increasing potassium excretion, the hydrogens will then increase in the blood. As the potassium goes out into the urine, the hydrogens have to go back into the bloodstream. They go in opposite directions. So therefore, when acidosis occurs, in other words, if you have too many hydrogens in your bloodstream, the hydrogens want to go into the cells. That's a form of compensation. It's going to do everything in its power to try and get hydrogens out of the bloodstream, which means some of it is going to go into the cells. But in exchange, potassium has to leave the cells to go into the bloodstream. So to fix or compensate acidosis, you're going to get hyperkalemia. Does that make sense? They go in opposite directions. And when you have alkalosis, meaning we got to put now, there's less hydrogens in the bloodstream, we have to put hydrogens out into the bloodstream. So you're going to put hydrogens from the cells into the bloodstream, correct that alkalosis, but in exchange, the potassium has to leave the cell, or leave the bloodstream to go back into the cells. Meaning we're going to have hypokalemia to fix the alkalosis. You've got to understand those mechanisms. Does that make sense? Okay? And this is just showing you the same thing in what I just said. Acidosis, all right, you give a lot of, so these dark purple balls over here are hydrogens, and the light balls over here inside the cell are potassium. So if you have too much hydrogen outside the cells, they're going to be put into the cells, but that means that the light blue or potassium goes out of the cells. So acidosis will lead to hyperkalemia, and vice versa. Alkalosis will lead to hypokalemia. Don't memorize, understand. Is that clear? And this is just showing you one of the cells in the collecting ducts. I didn't go into the details of the different types of cells in the collecting ducts, but this is basically what's happening over here. There's our carbonic anhydrase that's going to try and affect this. And you can see our potassium is going to go into the blood. That's where the bloodstream is. Potassium is going to go in here as hydrogens want to go out. They're going to go in opposite directions. Aldosterone, as I said before, as sodium gets reabsorbed, then hydrogens are going to get excreted. They also go in opposite directions in terms when we're talking about aldosterone. Okay, not in all the cells, I'm just talking about aldosterone.